So in light of recent scandals about elite colleges like Harvard and Stanford regarding the academic research integrity, where some professors are alleged to use fake data in their study. So today, we're going to look at that. So how do we use statistic analysis and visualization to check on the dataset and to detect possibly fake or suspicious datasets? Usually in academic study, you may have what is called a control group and experiment group, where this could be to study the effect of certain treatment method, new drugs, and other factors, so that you have some statistical analysis, and based on that, you want to draw certain conclusion. Now here, we try to study a certain teaching method and the impact of that to the students' performance measured by the testing scores. Like in many other academic studies, you may have 3 phases. The setup here, we're going to have control group and experiment group, where assume the first one is authentic. That is, you may have a Gaussian distribution. Here we have sample of 1,000 samples. Let's assume with your teaching method, with experiment, you may have an improvement on top of some base score distribution, and improvement is probably minor, right? Like 3 with a variance of 5. In the phase 2 of study, we artificially increase the improvement. Now in phase 3, we do similar improvement here, right? However, we're going to insert a score of 90 every 10 students of the group. That is, every 10 students in the index, we're going to put 90, which is a higher score. Of course, in the study, they may not use random number generator. They probably use the real control group, but upon the results, they may just do this data modification, prepare a data frame for easier analysis. All right, so let's run that. All right, so we have the data. Google Colab introduced a feature. If you have a Panda data frame, this is provided by Google, so that you can have the visual from the data set, right? So that you don't have to write Python code, the Google have the code for you. Right? Let's try that. For different phases, we have 1,000 samples in each group. All right, so this is a control and experiment, and this is control violin visualization for the control group and for the experiment group. Inserted 90 artificial improvement in the phase 2. All right, let's go to the statistical tools. Right now usually you want to compare the difference of mean. You may have a t-test, and the p-value will tell you if there is any significant difference or it's just from the random choices, right? So, and also the effect sizes, or sometimes Cohen's d. So that provides a measure on the magnitude of the differences between the 2 groups. So here, let's run that. And this is a t-test, right? With the actual value and the p-value here. And this is how to compute the effect size, the Cohen's d here. So we're going to print it out. And notice that here, the p is very small. So in phase 1 is 10 to -9. Here is significantly lower. That is 10 to -116. This is 10 to -21. Now, in terms of effect size, the first one is minor, second one is significant, and this one is medium, right? And here's some technical background. So this is a measure of effect size of difference between the 2 means. If the value is small, for example, like in this range, you consider a small effect, and this would be medium, it's 0.5, and then you may have large effect if d is 0.8 or higher. In the t-test, this is how we're going to test if there's significant difference between the mean of 2 groups. Calculation of the put STD, the standard deviation of the put samples, and this is effect size calculation, right? So let's look at the results. So all 3 phases have extremely small value. This indicates that the observed difference in the students' performance in the experimental group are statistically significant. That's the conclusion. In other words, it is highly unlikely that the observed differences is due to random chance alone. Now, given the extremely small magnitude of the p-value, especially in phase 2 and 3, one would wonder if the data has been manipulated to ensure statistic significance. Such minicore p-values are rare in real-world dataset. All right, so that's a red flag. Now here we have more than one. That's very large effect. Such a profound differences between groups might raise suspicion, especially when combined with extremely small value of p. And here in the phase 3 is medium effect size, suggesting a moderate differences between control and experimental groups. Now, when we look at the consistency across phases of study, right? So in phase 1, 2, and 3, we notice that it is notable inconsistency in terms of effect size across 3 phases. While phase 1 and 3 have relatively modest effect size, phase 2 has a very large effect size. If the new teaching method is effective, and we should see the consistent results. So one would expect more consistent effect size across phases. So this is another angle from which we may doubt on the data itself. Let's move to some other visualization. Let's run the code here. In these violin plots, we know that in the phase 1, they have slightly different, but distribution shape is similar, but in the phase 3, the 90 is inflated here. And here, the distribution is similar, but it's shifted. Significant difference of mean. Another angle of the data analysis on the data set is actually the distribution of it, right? Certain either physical or social phenomena could follow a well-known distribution pattern like Gaussian, binomial, or Poisson. And of course, with your data set, you want to study the basic statistical properties like a mean, variance, skewness, where kind of asymmetry nature of the data distribution, or kurtosis, that is this like a thin tail or fat tail kind of data distribution. From the distribution study, looks like this is the follow roughly the Gaussian distribution, except that there's some artificial inserted 90 here. So you may wonder, maybe I want to have another visual on that particular group, right? There is like negative kurtosis indicating the presence of fewer outlier compared to the normal distribution. That's phase number 3, because we have inserted this 90 here, right? 0, 4, right? So this status stand out here. This skewness here shows that is not quite symmetrical, right? So these two values of phase 3 will give you some clue about possible data manipulation. Let's actually plot the experimental group from phase 3. Highlighted 90 here is that is very like systematic, right? So in academic research, you could have this kind of a scrutiny with statistical analysis of the data itself, and this is so that we want to ensure authenticity of findings and maintain trust in the scientific community. Let's touch base on the ethical and practical considerations in the academic research, and some of you in the future will conduct research. The reproducibility is a cornerstone of scientific research. So sometimes one study with significant results is not conclusive. So that's why sometimes you require multiple researchers with a different setting, and if you produce similar results, that will be more credible. So there is what is called p-hacking and data dredging. That is, if you want to manipulate the data to try to get a good p-value, this will undermine the integrity of the scientific process and can lead to false conclusions. And another is that there are many other tools to test on the data authenticity, right? Probably want to use that some more advanced tools than what we introduced today. So that's it, and I will post the link to the notebook so that you can play the results on your own. Thank you.